Okay, hello, transmissions from the field. Not sponsored, but it's a very good. So I'm just mucking around, I'm just having fun. I want to make a collision system. I'm going to start really simple. Let's say we have a whole field of particles and there's a bunch of conditions to trigger a collision. As a particle moves along, either it can if it's in the rectangle of the screen area that we can see, it can either cross the screen boundary, in which case it'll reverse direction and bounce back, or it can run into another particle, in which case it reverses direction and bounces back. With everything, it's a great idea to just go completely naive, and so here is my naive implementation. I was actually surprised at how well this performed. I had to get up to about 256 particles on my MacBook Pro before it even touched 60 frames per second, which honestly, Python, a for loop with 256 elements, that's pretty good. So fundamentally, the way this works is we take a particle out of our, say, 256, and we check against the screen, and then if that succeeds, then we proceed to check against each of the other 255 particles. If it should trigger a collision with any of those particles, the for loop will break straight away. Otherwise, we'll continue checking until we've checked everything and then move. This is big O n squared, in the sense that every one of the n particles will have to test against every one of the n minus 1 particles. And the upshot of that is that, yeah, it performs pretty well at 8 particles, 16 particles or so. But if we were to double the number of particles, that would roughly quadruple the processing time, which is really not great. Although, for most retro video games, they will have probably less than 256 fully dynamic collidable objects. So for instance, in beat 'em ups or shmups or something like that, this approach would probably be fine and would probably be fairly numerically robust. If, on the other hand, you feel like you're leaving performance on the table needlessly, then there are other approaches which I'll look into. Okay, so another transmission from the field. Yes, this is the same day, 30 seconds after recording the last one, because I did my initial work in the morning, and then, like a weirdo, I went to a cafe and programmed up the next stage. Imagine that. I go to another country and I just go code in cafes like a nerd. Well, to be honest, that's what I would have done in Australia. Anyway, so the next step is something called spatial grid or spatial hashing or something like that. The basic idea is that we have our window space, which contains about 256 particles, just as an example, and then we split that into rectangles. And for each particle, we can take their position, divide it by the grid size, and that'll give us an integer, and that is the index for the row and column of the little sub box that the particle is within. This has the benefit that a particle now does not have to check against all other particles, but only checks against particles which are nearby. This can be fine-tuned. Reducing the grid size will improve the performance, in theory, in the sense that each particle will be checking against a smaller number of particles. However, one issue that I ran into is boundary cases. So I found that particles had a tendency in the long term to actually get stuck on the boundaries between boxes, and I'm not entirely sure why that is, but I'm about to sit down and work through that problem and try to come up with a more comprehensive solution. Overall, this method I feel is pretty good. There is always, I'm doing a full spatial grid, so I'm just straight up dividing the whole space into boxes. There is the possibility that some boxes will have no particles in them, but the overhead in this case, I feel, is minimal. I feel like it's manageable. So yeah, that was the sort of stage 1 optimization. Okay, so that wasn't actually as hard as I thought it was going to be. The basic approach is that I have my grid with a whole bunch of boxes, and for every particle, my list of particles, I can quickly calculate which box, which row and column box that should belong to. Now, when I go to update, that is based on the number of particles. It's linear in the number of particles. So I step through my particle array. One particle at a time, pick the particle, work out which box it's currently in, remove it from that box so it's an orphan, and then based on where it is and which direction it's moving, we get like 1 or 2 boxes that we want to check. So then we run the naive check on those 1 or 2 boxes, and then we go in another direction. There might be another 1 or 2 boxes to check. We go ahead and do that. And finally, after we've done our move checks, we update the particle's position, throw it into its new box. And I'm running this at the moment. There do not appear to be any numerical errors like I was seeing in the previous attempt. And performance-wise, I'm seeing about 950, 970. Anyway, I'll call it more than 900 frames per second. So we've gone, what is that? A 15 times speed up? Anyway, we've gone from about 65 frames per second to about 970, 950 or so. So that's a big win. I was going to look at sparse spatial grids, but I don't know if there's really a benefit to that. I mean, in the sense that my collision check is already linear in the number of particles, and it's a constant operation to calculate which box the particle is in. And if I have extra boxes which are unused, yeah, I guess you could say they slow down the fetch operations, but I'm pretty happy with this for now. So this stage of taking our sort of soup of particles and then imposing a structure, an acceleration structure on top, is called the broadsheet stage of collision detection. In other words, we're sort of broadly detecting which objects could possibly collide. As a matter of fact, with my particles, I'm not using accurate collision detection at this stage at all. I'm simply basing it on the taxicab metric, that is sort of the rectangular distance, absolute x plus absolute y. And so what we could do in future sessions is look at a hierarchy of tests from a less accurate to a more accurate test. I'll probably look at that. That sounds like fun. Anyway, thanks for hanging out. I know it's been a little unorthodox, but I will see you again soon. Bye.